we're working on quantum tunneling, and this will be really fast because don't have a complete amount of time. But we're just going to get right into it. This will be a fast one because there's not that much to this. So, if you remember from last time, we're dealing with the Schrodinger equation. We have negative h bar squared divided by 2m times second derivative of psi respect to x plus v of psi is equal to e of psi. Now, when we were last doing this, we pretended like v here was equal to infinity and v here is equal to 0 to make it simple. So we didn't have to worry about v, we only had to worry about the derivatives. But this time, we'll be dealing with a situation where that's not quite true. So, what happens when v is not equal to 0 or infinity? Well then, I better move this out of the way. I want to hold on to it though, because it's a very nice equation, very important. So we're gonna stick that up in the corner. We'll shrink it to hopefully it's mostly legible. Hang on. Yeah, that should do. Keep that up there. That's pretty important. Instead, we're going to pretend, obviously in this end, we'll pretend like v is equal to infinity here. I have like a wall, but then we'll have a non-zero v, where v is something, and then v is equal to 0 again. Now, what is the analogy for this? The analogy would be like, imagine if we have, a hill like this. I have like a ball. Hang on. Gotta make it same color. Let's imagine I have a ball here. If we try to push it up the hill, if it has enough energy, it'll keep on going. But if it doesn't have enough energy, it'll actually come back down. However, because quantum waves or probability waves, we'll treat them like waves. So if you can imagine, we have like a loudspeaker that emits sound waves. You can encounter a wall, say of bricks, and when it encounters a wall, it'll be weakened over time because of the thickness of the wall, and then it'll come out the other end like so. And this is the analogy we're going to use for our wave functions. Although as a slight note, I'm just going to write the equations above hand. So if we have a wave, like last time, we'll call this sine, we'll call this A times sine, where A is just some constant that I guess you could say boosts or strengthens the sine wave. Then we'll have here inside the potential an e to the negative x. There's a reason for that, which I'll get into in a minute. It has partly to do with derivatives, partly have to do with the things, but that's not worth it. And on this end, we're going to have another sine wave, but it's going to be lower. So I'm going to call it B sine of x. I better add that x. Don't forget your variables. Thing. There we go. Now, and here, as you can hopefully tell, here we're most likely to find the particle. So probability is at the maximum. And here, probability is a minimum. And here in this e to the negative x bit, probability is decreasing. I don't know how to abbreviate decreasing, so I'm just going to draw an arrow. Because if you think of this wave as representing probability, we're most likely to find it here inside the well, and we're least likely to find it here outside of the barrier, and here it diminishes with distance. We're more likely to find it here than we are here, and that's not a surprise. And by the way, this is partly relevant for all the derivatives we learned earlier. The reason why we're using e to the x. If we have, hang on, wrong pen. If we have d of e to the negative nx with respect to x, this will just become negative n times e to the negative nx. And as you can see, we have this term is preserved. And if you remember anything from the last time when we were doing the Schrodinger equation, you might remember that all the side terms have to cancel out when we're doing something like this. And since this e to the nx term remains, this means we can cancel out, if we have the v psi equals e psi and other psi's, the psi's will cancel. These will all go away, leaving us only with this bit, which is why we choose e to the x instead of something like, negative x squared. If it looks like d over dx of like negative x squared or something, that just becomes, negative 2x, and x squared is nowhere to be found in this term, so it won't cancel out later. Anyway, what does this have to do with real world scenarios? Because that's cool physics, right? Well, let's imagine that we have a proton, stuck inside the atom of, say, a uranium atom. You can imagine the uranium atom's walls as being a bit like the barriers. So of course, like uranium of the left, for the left barrier, this would be uranium inside, and this would be the right side of it. So uranium right, and this is beyond, because as you might recall, uranium atoms can eject particles like protons or neutrons, and this is because of quantum tunneling. I'm gonna move this. Hang on, give me a minute. Nope. There we go. Anyway, so if we have this extending outward like that, if psi of the proton looks like this, we can have a the highest wave function inside the uranium atom, and then we can have it decrease as it leaves the barrier, and then we have a wave function that proceeds out of the uranium atom, which means that most of the time the proton remains inside of here, but sometimes it can be ejected, and we can find it over here or over here. which is far away from the uranium atom. And obviously, there's more uses than like the fission of nuclear particles, as roles in like radios and many other reasons. If we'd be here forever listening, but this is just like the concept of quantum tunneling. It's just that like uh, for non-infinite barrier, uh, there's a chance of finding a particle beyond the barrier. And so that's what all this looks like. Anyway, that's it for now. Uh, derivatives will come back, sort of, but next time we'll be using integrals and investigating how they are relevant to quantum physics. Anyway, see you next time.